Okay. Do you see the screen?
Yeah,
okay.
that's perfect. Thanks.
Okay, so good morning, good afternoon, everybody again. Let me start thanking the organizers for the invitation. Nice invitation. It's a pleasure to be here today. So as you can see from the title, I will be talking about super non-Abelian T-duality and potential obstructions. This is basically what I've been working on during my PhD with my supervisors Silvia and Martin, and also in collaboration with Dimas Orokin. So let me just start with a brief outline of what I will be discussing. So I will first try to briefly introduce the topic, so T-duality in general. I will try to give a kind of highlight some features of it. And then I will describe the general dualization that one can perform for the principal chiral models, and then specify a specific model, namely the principal chiral model on OSP1/2, which we took into account and we kind of studied in details. And then I will go back to the kind of more general picture. We'll try to take again a more general point of view and discuss the dualization of coset models, and specifically of two classes, namely symmetric and semi-symmetric spaces. And then I will try to and here I will mention some these potential obstructions that you saw in the title, which appear in these coset models, and then I will try to wrap up and draw some conclusions. Okay, so let me start by saying that in physics, when we use the term duality, we usually have in mind the possibility of describing a certain physical system from different points of view, two different perspectives, which are sometimes complementary to each other and can give interesting points of view on a physical system. And in the literature, in the physical literature, and also in the mathematical literature, probably in the last decades, a lot of dualities have emerged and have been studied and introduced, and target space duality, which for short is also T-duality, is one of these. And this arises in the context of a sigma model. It has the feature of relating different background geometries. And for this reason, it has played a very important role, a prominent role in the context of string theory framework, where it was actually initially uncovered, where these sigma models are used to describe propagation of strings. So let me say that there are various points of view on T-duality. The one I will be taking here today, it's the kind of, in a sense, the canonical one, let's say, the one that was introduced in the early 90s, and can be somehow summarized in terms of a sort of algorithmic procedure. So let me try to summarize this procedure, and this is what I will have in mind when talking about T-duality. So one generally considers a two-dimensional sigma model, which is defined on a certain background with a group of isometries G, and the procedure basically consists into the gauging of a certain subgroup K of the group G of isometries, and in the modification of the action by introducing a term which enforces the flatness of the gauge fields that we just introduced in order to gauge the isometries. And this can be performed by means of Lagrange multipliers. So there is this term which appears in terms of Lagrange multipliers, and this step is important because it basically allows to recover the initial model under suitable assumptions on the worksheet topology. One can indeed completely remove the gauge fields and recover the initial model. While on the other hand, one can perform the integration of the gauge fields, so remove them from the action, and exploit the K-gauge freedom to remove the degrees of freedom from the initial model. And this way one lands on another sigma model, which is said to be T-dual, and which has now the feature that basically the Lagrange multipliers that were introduced in the second step now play the role of dual coordinates. So this is kind of the algorithmic step that we have in mind, that I will have in mind when talking about T-duality. And from this algorithm, it is kind of already visible that the group of isometries G plays a very important role in this context. And indeed, there is immediately one important distinction that we can make in terms of these, which concerns the group of isometries. So T-duality has the feature that it generally reducing the amounts of isometries of the background, and in particular only those isometries which commute with the gauge ones usually survive dualization. So in terms of this, one can recognize that backgrounds which have a single isometry or multiple commuting isometries will have the feature of preserving this set of isometries in the dual model. So the dual model will again have the same group G of isometries, and one could perform the gauging procedure again, and by means of this gauging procedure recover the initial model. So from this point of view, T-duality is regarded as an exact symmetry of string theory, while on the other hand, if we consider a background with a non-Abelian group of isometries, this group is generically reduced to some smaller subgroup, or in some cases actually also to no isometries at all. So in this case, it's still not clear. There is no clear way on how to proceed in order to perform the gauging again and going back to the initial model. So in this regime, T-duality should rather be understood as a relation between equivalent theories rather than an exact symmetry. So from this point of view of the isometry group, one can, roughly speaking, draw sort of a landscape of T-dualities. Well, highlight at least 4 main regimes in which it's possible to work. As I said, this is not an exhaustive picture because there are other approaches to T-duality, but this is, roughly speaking, the 4 regimes that one can highlight in this from this algorithmic procedure, which is kind of the canonical picture that was initiated in the late 80s and early 90s. So, in the first regime is the Abelian bosonic one, in which, as I said, the group of isometries is bosonic and is Abelian. And by means of the gauging procedure of Givian and Rocek, this was the gauging procedure that I mentioned earlier, which was introduced in the early 90s. This regime was soon generalized to the non-Abelian bosonic setting by Quevedo and Dalosa in the early 90s, very soon. And then this was successfully studied and exploited in various ways in the subsequent years, and it is still nowadays a very active field of research. And it was only more recently, namely in 2008, that Berkowitz and Maldacena introduced the possibility of kind of generalizing this setting to the possibility of having fermionic backgrounds, and in particular to the case of having an abelian set of fermionic isometries. And this was studied in 2008 by Berkowitz and Maldacena, and also in this other paper by Beisers and other in kind of quite in detail. And well, from these 3 regimes, it is kind of it is natural somehow to think about the 4th regime, which is the super non-Abelian one, in which basically one has a supergroup of isometries which close on a certain superalgebra. And this regime is it's kind of so far the least studied and understood, even though there has been some work in this direction, especially by these works that you see here. But nevertheless, it's still the least studied, and in particular, there are kind of few examples available in the literature, explicit examples of this. So this is the reason why we decided to concentrate on this regime. And well, now let me try to give some motivation and some reasons why the other regimes have been kind of important, which also support the importance of this 4th regime. So the abelian setting has been, among various things, has been very relevant in proving the self-duality of certain notable backgrounds in the context of string theory, in particular under the combination of abelian bosonic and abelian fermionic isometries. And particularly in 2008, this was used to prove the self-duality of the AES5 process-5 background, which helped uncovering a peculiar feature, which is this dual superconformal symmetry, which had been observed and in previous papers. And so this self-duality was proven using this combination of abelian T-dualities. The bosonic non-Abelian case, as I mentioned, this due to its peculiar nature, actually people tried to develop new techniques and new approaches. So they started taking new perspectives, which are still nowadays very active and very interesting fields of research, such as, for example, the Poisson-Lie T-duality, trying to give a duality invariant descriptions of these sigma models. But nevertheless, despite its features, this regime has played still a very important role because it has been successfully exploited, in particular since 2010, I would say, as a solution generating technique in supergravity, and also from this as a technique to kind of consider new examples of holographic pairs. So this also kind of gave birth to this interesting relation and interplay between T-duality and holography, in which basically people try to consider to generate new supergravity backgrounds and try to consider their holographic dual in the dual model. Also, more recently, this non-Abelian T-duality has been put in close contact with the formations of integrable models. So there is an interplay with these integrable models as well, and in particular with this lambda deformations, since the work of Svetsos, and a bit even more recently, also in connection with Yang-Baxter deformations, which I think specifically, especially in these three works by Linus and Ricardo, they highlighted this relation, and this is actually also where they gave some. They kind of studied also this super non-Abelian approach. Okay, so this kind of set of motivations, this kind of successful exploitations of this non-Abelian bosonic setting somehow represent for us and kind of a sufficient condition, or at least a motivation to try exploring more this super non-Abelian setting, because one could hopefully extract novel information in these from the study of these super symmetric models, and so we try to focus on our attention on classes of models which are constructed out of starting from these supergroups. And again, as I said, we consider mainly three classes of models: principal, chirals, and coset models of the symmetric and semi-symmetric type. And well, also in this regime, and also we checked kind of explicitly again that this feature, which is typical of the bosonic dualisation of preserving integrability and actually by means of exchanging the role of equational motion and Maurer-Cartan equations, is kind of retained. So now let me try to move to the description of the principal chiral model, to the dualization of this model. So principal chiral models are a very kind of interesting class of models, which is also kind of simple in a sense. And they are basically two-dimensional signal model on a certain Lie group or the supergroup G. And these are defined in terms of this action that you see here, where J is the Maurer-Cartan current, defined in this way. And this bracket that you see here is just the inner product between the generators of the algebra, and this star is the odd star on the worksheet. And these models enjoy kind of a large set of isometries, which kind of derives from the left action of the group and from the right action of the group, and these are the associated intercurrent. Also, these models have another interesting feature, which is that they are integrable, classically integrable, and this feature comes from. I heard a voice.
Okay.
Okay.
Yeah. Sorry.
Okay.
You can continue.
So these two conditions can be encoded into the flatness condition of what is known as a Lax connection, which depends on a spectral parameter Z, and basically it encodes an infinite set of conserved charges, conserved quantities, and this is the hallmark of classical integrability, and this is why we say that this model is classically integrable. Okay, so there is another ingredient that we took into account in our analysis, which was initially introduced in these papers that you see here, and this is a topological deformation, which can be introduced to deform these principal chiral models by means of a Lie algebra 2 cocycle. And this is to be topological because it doesn't affect the local physics, and it leaves invariant, leaves unchanged the equations of motion and the construction of the Lax connection and all the isometries. So, well, we shall actually consider just to mention this with this Lie algebra endomorphous D, which can be associated to the 2 cocycle by means of the inner product, And this has the two important properties which are inherited by the gradient antisymmetry of omega and the two-cocycle condition, which is that this is antisymmetric with respect to the inner product, and it acts as a derivation on the Lie bracket. Okay, so let me now describe the gauging for these models. So I said that this model have a large set of isometries, this G left cross G right. And well, we performed the gauging for the G left sector of the isometries. One could perform the gauging as well for the right part. But well, it is common to consider the left sector. There's no particular preference. We just went for this. And well, we just gauge a certain subgroup KL of this isometry group. And we do the gauging by introducing this gauge field, covariantizing this current with gauge fields omega, which take values in the KL algebra. And now J omega, the covariantized current, is invariant under the local KL transformations, which are the ones that you see here. And now one can enforce the flatness of the gauge field by introducing these Lagrange multiplier terms. And this is the modified action, which we also included this B field term. And you see this is the Lagrange multiplier term, and there is also this extra term here, which is there not to spoil the action of the right action of the group. And this way, the action is invariant under the KL gauge transformation, provided that the Lagrange multiplier is transformed in this way. So one can conveniently rewrite the action in a kind of a slightly more compact way by defining these tilde multipliers, and this is kind of the master action from which one can recover both the initial model by integrating out the multipliers, or the dual model by integrating out the gauge fields. And then one has to fix the K gauge invariance in order to get rid of the extra degrees of freedom and recover the same amount as degrees of freedom that were present in the initial model. Okay, so let me describe the variation of this action. So if we perform variation with respect to the gauge fields omega, we find this set of equations of motion where we define this kind of covariantized D with combining D with the adjoint action of lambda tilde. And this equation can be solved kind of in general for J omega in terms of by introducing these operators, 1 or 1 plus minus D lambda tilde, which are just formal series expansion of this operator D lambda tilde. And these P plus and minus are just the projectors on the worksheet. Okay, then one can substitute this J omega back into the action and can do a bit of manipulation and rearrangement, and the action can be rewritten in this form that you see here. And actually, probably more conveniently, one can introduce a set of dual field binae, which you see written down here, in terms of which the dual action takes kind of a nicer form. And specifically, one can see a T-dual metric term, which is this E star E, and a B field term appearing in the action in terms of this D lambda tilde acting on the field line. Okay, so let me now describe this exchanging role of the equations of motion Maurer-Cartan equations. Well, if we perform the variation of the action of the dual action with respect to the dual coordinates, we obtain Maurer-Cartan-like equations of motion, where these are the equations of motion with J replaced by J tilde, and J tilde being just basically the J omega that we had found in the previous slide. And then, since J omega satisfies by construction, J omega or J tilde satisfies by construction this equation, which is the one from which we actually derive this expression, and we can combine this information with Jacobi identity to recover the conservation equation for J tilde. And so this exchange in role allows to construct the dual Lax connection formally as it was done for the initial principal chiral model, with the replacement of J by J tilde and some Z tilde, some in principle different spectral parameter. So let me now mention just one more thing about these principal chiral models, and then I will move to the description of the specific case of OSP1/2. So this is this concerns the residual set of isometries that we expect to find in the dual model. As I said, we are gauging the left sector of the isometry group, so we expect in the dual model to still find the right sector of the isometry group. And indeed, one can see that under the right action, the right action induces this transformation of the Lagrange multipliers, and the dual action is manifestly invariant under this transformation, and indeed one can construct the dual Noether current associated to this residual set of isometry. So as expected, the right sector of isometries is still present in the model. Okay, so this is basically all I wanted to say regarding the dualization of principal chiral models in general. So I would now move to the dualization of the specific case of OSP1/2. So let me start briefly with some sort of motivation for this model. Well, first of all, this is kind of a simple model, clearly, but the thing is that this is not only a simple model, which one obviously wants to start with in order to construct some explicit examples of super T-duality, super non-Abelian T-duality, but it also has some actually interesting features. So in particular, it can be interpreted as an appropriate supergravity background, and specifically as a supersymmetric version of ADS3. And also another nice feature is that if one considers only the purely bosonic part of this model, which is the principal chiral model on the SL2, basically this model was considered in the early 90s in this paper by Alvarez and others, and the T-dual model to this principal chiral model was interpreted as contains a B field and a metric, and it was interpreted as the metric was interpreted as a black hole. And so for this reason, it is somehow interesting to wonder whether there might be the possibility that by performing the dualization on OSP1/2, one might be able to interpret the T-dual model as some sort of supersymmetric black hole, or some black hole in a three-dimensional supergravity theory. So to study this model, we just start the initial setup is basically considering the OSP1/2 algebra, since in the end we basically consider everything in terms of these bunch of commutators, in terms of which the dual action and dual field are written. So this is the OSP1/2 algebra, which has 3 bosonic generators and 2 fermionic generators, and these are the inner products among the generators. And also importantly, H2 vanishes for OSP1/2, so we worked without any deformations. So we basically, all the expressions that I gave earlier kind of simplify because we basically set D or omega to 0 in this model. So first of all, let me start mentioning that the initial model, since it's a supergravity, appropriate supergravity background, satisfies the supergravity torsion constraints. These are a set of constraints that kind of any superspace should satisfy, is required to satisfy in order to be given the appropriate interpretation in terms of a supergravity theory. And these were initially introduced in order to establish a relation between the superspace approach and the component approach to supergravity. And basically, these constraints are constraints on the torsion and on the form of the connection. And if one consider the Cartan structure equations, basically one can impose these constraints and verify whether they are satisfied or not for a given choice of field bind and connection. So in particular, in this three-dimensional case, this is the form of the constraints, where this E alpha beta is the bosonic field bind and this E alpha is the fermionic field bind. And we see here in the first equation, this is the kind of the most restrictive constraints, because here, as you can see on the right-hand side, there is no free component of torsion, while in the second equation, we have some free component of torsion that can be kind of, remains unconstrained. In the first equation, there is only one component, non-vanishing component of torsion, which is constant. It's said to be a constant. And this constraint is kind of the most restrictive one, and it's basically the statement that any curved superspace should contain the flat superspace solution in order to be given an appropriate interpretation in terms of a supergravity theory. So the initial model satisfies nicely these constraints by it is sufficient to look at the Maurer-Cartan equations in order to see this. So in particular, if we decompose the current on the generators L alpha beta and Q alpha, and we look at the explicit form of the Maurer-Cartan equation on the two projections of the Maurer-Cartan equation, they take this form here. And you can see that these two equations can be mapped to the above ones by choosing field-bound and non-vanishing components of connection and torsion in this way. So the initial model satisfies these constraints in a kind of a simple way by construction. So now we construct the T-dual model by gauging again the OSP1/2 left sector of the isometry group. And since we are gauging the full OSP1/2 left sector, we can exploit the K-gauge freedom to set the initial to get rid completely of the initial coordinates, and this way the multipliers lambda tilde simply reduce to the lambdas, which take value in the full OSP1/2 algebra. And I will also mention very quickly the dualization of the purely bosonic subsector of this OSP1/2, which is SL2 left, basically. And also, since we remove the deformation omega, this implies that this d lambda tilde just reduces to add lambda, and so the T-dual action is simplified in the way that you see here with this set of T-dual field lines. Okay, so looking at this action and this choice of field line, one can immediately construct. Well, this is the definition of the B2 that we can extract from this dual action. One can construct the modified Maurer-Cartan equation that this set of dual field lines satisfies. As you can see here, there is no zero on the right hand side. There is this operator here acting on this commutator of field line. And this is the structure of the H3, which is constructed by taking the derivative of B2, in which also this operator appears. And this is something that, as I will now describe, will kind of give us some troubles in a sense in interpreting the dual model, in checking the torsion constraint for the dual model. So if we want to study the torsion constraint for this dual model, well, we can start by expanding the T-dual field line on the basis of the algebra generators and computing this commutator. And basically, we start by analyzing the L alpha beta projection of the torsion constraint, since, as I said, it's the most restrictive one. In order to study these constraints, we can see, if we look at this equation, that here, as I said, there is this constant term, and here there is the E alpha wedge E beta. There's only an E alpha wedge E beta term appearing. So we can see that in order to compensate for this term on the right-hand side, which is constant, on the left-hand side, here we have this E gamma alpha, and if we expand the connection on the field line, we will have a fermionic and a bosonic component. But this term here will never be able to compensate for this constant term on the right-hand side, because simply there is no E alpha wedge E beta term. There is no fermion term. So whatever should be able to compensate this term on the right-hand side should come from this exterior derivative of the field line. And in particular, we can compute these by exploiting the equation that I showed you in the previous slide. And so we can proceed by computing basically this exterior derivative by means of this equation, and taking the projection L alpha beta and concentrating on these terms that appear here in this commutator. So if we do this, well, the problem is that we find that the structure of these terms is not constant at all. So there is basically no way of canceling this term here and of basically satisfying the equation. So this hints toward the fact that the T-dual model spoils the supergravity requirements. And also, actually, there is another hint toward this fact, which is that, as argued in this paper, three-dimensional supergravities should have a tree form which has a specific structure in which only certain components appear, and in which these certain components are written in terms of certain scalar superfield. And using the equation that again I showed in the previous slide, one can compute explicitly the H3, and in which again there is this operator which appears, this 1/1 minus add operator which appears, and one can immediately notice by just looking at the first few terms that there are contributions to this H tilde gamma beta alpha, which should be a not allowed term. So again, in this sense, the model seems to violate the above structure. So before kind of surrendering to this result that the dual model is not satisfying the supergravity requirements, we also try to perform some local OSP1/2 rotation of the field bind in terms of these G element or OSP1/2 element local on the worksheet. And these terms, this rotation has the property of leaving the metric invariant while adding some extra contribution to the B field. So one could in principle hope that this extra contribution might be such that one could fix the group element G in such a way that the torsion constraint is successfully satisfied, and also the requirements on the tree form. And so if we define these rotated multipliers, this lambda G, we can look at the modified structure equation, and we can again kind of perform, well, where we define this covariantized derivative nabla A and this A in terms of this group element G, and one can again kind of play the same game that we did before this rotation. So we can try to compute again the projection of this rotated field band on alpha beta, and what one finds is that while certain unwanted terms can actually be removed from the torsion constraints, there are still terms which cannot be removed. So again, this hints toward the fact that the T-dual model is probably not able to satisfy these torsion constraints. And possible explanation, probably an explanation for this, well, also, as I said, I should mention this, this incompatibility also arises in case one dualizes only the maximal bosonic subgroup SL2 R left of OSP1/2. And well, probably the reason for this is that an explanation for this is that the model was kind of too simple in a sense. It was not a proper three-dimensional Grishwars superstring, as these models have been have been shown to possess a nicer compatibility with supergravity, and in particular to preserve the supergravity torsional constraints under T-duality. And so for this reason, it would be interesting as possible and possibly and hopefully as some future work to study the proper generalization of this model to some three-dimensional Grishwars string. But this would, however, require the modification of the techniques that we adopted in this gauging procedure, because there are some obstructions which appear in this case. So one should accordingly modify the procedure, and well, it would still be certainly interesting and instructive to consider this. And also, there is actually another interesting thing that we kind of noticed more recently, and with which this impossibility of satisfying the three-dimensional torsional constraints might be related, and this is something that was kind of already observed in the dualization of compact spaces in this paper from 1993, and more recently was also discussed by Bielli in a paper from 2021. And this is that basically under T-duality, there is kind of a breaking pattern which takes place, which, for example, in the case of compact spaces, basically the breaking pattern goes like this: as 3 is broken into some 2 sphere, which is fibered over some interval. This R, it's kind of a semi-infinite line, and well, this very same pattern can be detected not only for the case of ADS3 with the similar breaking for ADS2, but as well for the case of OSP1/2. Indeed, the bosonic sector at least can be, since the bosonic sector is just ADS3, and one can observe this pattern from by performing an appropriate change of coordinates. And so the natural question is whether this breaking pattern might somehow be also extended to a supersymmetric setting in which one goes from super ADS3 to some super ADS2, which now has these prefactors which also depend on the theta's. And well, we are now trying to work in this direction, and so far the main problem has been trying to identify an appropriate parameterization of super ADS2, and we have been trying to do this by comparing to this paper of Berlinde from 2004, in which he constructed the supersymmetric ADS2 as the coset OSP1/2 mod SO1,1. Which is actually something that I will mention in the next few slides, because it's one example of semi-symmetric spaces that I have been considering. And well, so far it seems that this kind of super ADS2 should be present in the model, and actually we are now also wondering whether also the B2 fields from this semi-symmetric space might also be matched in this after this dualization procedure. And this would be an interesting feature, because somehow it would mean that the dualization brings the principal chiral model into some semi-symmetric space plus something else, some semi-symmetric space on a lower dimensional, so in 2 dimensions rather than in 3 dimensions, plus this interval, which here I wrote as dr, but well, in superspace this might possibly require some appropriate generalization, which we still need to clarify somehow, something which could possibly be interpreted as some super interval. And so this is.
Sorry, can I ask a question there?
Sure.
So that thing that you wrote down in the second equation, as you said, this is
one?
like it's like the super interval, right?
Yeah. This is something that we are thinking which should have somehow some generalized interpretation. So in the bosonic case, it's an interval. In the fermionic case, we're thinking this should be some supersymmetric generalization of the interval.
Okay, yes. So in that sense, also you would like to bound that interval, right? Because say for holography, you require, in the best of the cases, to have a compact space.
Yeah.
So you will have, say, if you start with some ADS3 in the case that Daniele analyzed, you have ADS3, then you go to ADS2 times an interval, and you would like to have that as a compact space in such a way that you can realize an holographic model. I suppose the super non-Abelian will have the same problem, right? Of
Absolutely. Yes. Yeah. So the thing is that if you assuming this matching works, if you set the fermions to 0, you should recover the purely bosonic case. So you should recover no results. So in this sense, it will be affected exactly by the same problem. And the thing is also that we don't really exactly know at the moment what this super interval might be. We don't even know how to write this super interval at the moment. We have some vague idea, but we are still trying to figure out, actually, because so far we have been having trouble with already with the matching of this super ADS2, because we couldn't find a lot of kind of literature regarding this super ADS2. And basically the only source that we found was this paper of Berlinde, which is actually something that again, as I said, I was already looking at for the dualization of OSP1/2 as a mod SO1,1 as semi-symmetric space. But this also required some work, because he doesn't give like an explicit expression for this super ADS2 metric. So we kind of found some trouble in trying to get a proper parameterization of this super space. But well, it seems to be kind of working, but we still have to complete the full matching and to find an interpretation then for this supersymmetric interval, assuming we can call it a supersymmetric interval, or maybe there is some other interpretation in the literature that we're not aware of yet. It could also be, I don't know, to be honest, at the moment. But yeah, certainly. Yeah, sorry.
Yeah, sorry, go ahead.
No, yeah, I was just saying, yeah, sorry, certainly this requires some kind of generalized interpretation. So one needs to better understand and clarify this point. Absolutely.
Okay, and another very naive, because, or let me try to see if I am understanding what you said, because you said that the torsion constraints are not satisfied for the
Yes.
super non-Abelian T-dual.
Yes.
So what I understand is that the non-Abelian T-dual, it maps equations of motion to equations of motion, and therefore is a technique generating solution in its full. For fermionic T-duality, non-Abelian version, I do not know if that is the case. But then you are saying that whenever you combine both, then you basically you do not map solutions to solutions, or
no, well,
am I
so
wrong?
the thing is that in certain cases you do map solutions to solutions. So, for example,
Okay.
in semi-symmetric models
Okay.
and in Green-Schwarz models, there are these papers that I mentioned earlier. Yeah, these ones basically, in which it has been shown that these solutions are mapped to other solutions, at least under certain requirements of the algebra. And the thing is that in this case, this seems not to happen, but the reason might be indeed that this is kind of a too simple model, because this is not a three-dimensional Green-Schwarz model. And what seems to be happening here, if this matching works, it's kind of a, well, at least to me, it's kind of a peculiar feature in a sense, is that this three-dimensional supergravity background is mapped to something which is again a supergravity, but in a lower dimensional setting, in a sense, because these OSP
exactly
1/2. Yeah. So in a sense, this is in a sense, if this matching works, this is kind of the interpretation I would give. So we were not able to solve the torsion constraints because we were considering a three-dimensional superspace in the dual model, but the torsion constraint might be actually only satisfied in some two-dimensional subspace.
Yeah, and I think in that sense you will have room for the explanation of the super interval.
Yeah, exactly.
You will have a 2D model times this semi-infinite interval, and then there will be room for.
Yeah, exactly.
I do not know what is like a super interval, but maybe in there you will find something.
Yeah, exactly. We don't know yet at the moment, but yeah, I think it would be interesting to clarify this point, to better understand this. And personally, I would also find this result interesting, of this mapping from a three-dimensional to a two-dimensional supergravity. Because the thing is that if this matching works, and if the dual model can effectively be rewritten as a semi-symmetric space, this is by construction somehow a proper Green-Schwarz strings, and it is kappa symmetric, and it has all the kind of necessary requirements that it has to be a proper supergravity background. So if the matching works with the model of Berlinde, it's somehow automatic in this sense, that it is a good two-dimensional background. And then there is this, as you said, there is this room to play with the interpretation of the superinterval, which is not clear yet. I don't know yet. We don't know, but maybe there is some nice interpretation that could be given on this. Absolutely, I hope so.
Okay, thank you.
No problem. Thank you. Okay, so yeah, well, this is, I guess, all I wanted to say regarding this model. So now I wanted to move to the description of the other two classes of models that I mentioned, these cosets, symmetric and semi-symmetric spaces. So let me just try to go through the dualization for this model, and which is basically the same as for the principal kernel model, except that there are, as I said, some complications which may arise that I will try to highlight. So let me just introduce these symmetric and semi-symmetric spaces. These are two interesting classes of models in which the subgroup H arises as a fixed point set of an automorphism acting on the algebra. And this is of order 2 for the symmetric spaces, and of order 4 for the semi-symmetric case. And this basically imposes some orthogonal decomposition of the algebra and some restricted set of commutators. These are the commutators for the symmetric, and these are for the semi-symmetric. So what happens for semi-symmetric spaces is that the subspaces P and Q happen to be the fermionic subspaces, while H and M happen to be the bosonic subspaces. And one can see that if one formally removes, sets to zero whatever lies in the subspaces P and Q, well, basically the symmetric case is kind of recovered. Also in terms of these commutators, if we formally remove whatever lies in P and Q, we just recover the commutators of the symmetric case. So for this reason, I will only kind of describe the dualization of semi-symmetric spaces for brevity and to avoid redundancies, as basically one could rewrite all the expressions for symmetric spaces by formally removing and setting to zero whatever lies in P and Q. Okay, so this semi-symmetric decomposition in terms of these four subspaces reflects on the structure of the current, which as well decomposes on these four subspaces, A, P, M, and Q, which we call with the same names as the decomposed algebra. And in turn, this also reflects on the transformation laws under the local HR action. And this implies that basically it's the A component lying in H, which transforms as a connection, while the P, M, and Q components transform adjoint. And so constructing a local HR invariant action and also a global G left invariant action requires basically using these P, M, and Q components. And this is the standard canonical form of the semi-symmetric spaces action, in which this MM is a metric term and this PQ term is kind of a B field term, and this action is of the kind of the Green-Schwarz form, and this is why these models are kind of so played such an important role in the context of string theory, and also these models exhibit integrability and kappa symmetry. So this is why these models are kind of very peculiar and very powerful, and have appeared so many times in the string theory literature. So let me discuss again this integrability property. So in this case, one can compute the equations of motion of these models which take this form here, and also the Maurer-Cartan equation, which is again just the flatness for J, can be decomposed on the four subspaces. And so one obtains four equations now. Again, as I said, if we set to zero whatever lies in P and Q, we recover whatever the equivalent for the symmetric case. And well, these seven conditions can be combined can be encoded into the flatness condition for what is again known as the Lax connection, which again depends on this spectral parameter Z, and this again represents the hallmark of integrability for these classes of models. So, as I said, these models are very peculiar, and here I just wanted to very briefly mention how this grading of the algebra imposes basically some strict condition on the one forms on J, so that basically one can see kind of in a clear way that these J satisfy, this field bind satisfy the torsion constraints. So if one takes an explicit basis for the algebra, by explicitly writing the indices and introducing inner products, well, one can write down the splitting of the Maurer-Cartan equations in this way, and we basically see that now the torsion constraint that I mentioned earlier are kind of trivially satisfied in a sense, because this is the M is the bosonic field bind, and here on the right hand side we only find these constant components of torsion, which are written in terms of these structure constants. And similarly, it happens for the fermionic field bind, which has these non-vanishing components of torsion. And also, this one can look at the B field, which also has a nice structure in this case, and only exhibits these two components done here. And so this is kind of all the result of the grading, and this is why this also another kind of observation in terms of which one can see that these models kind of have very special features, which makes them fit very well with this supergravity picture, and this is why probably they have happened to be so powerful. So let me now mention some more general features of these models and of the dualization of for these models. So one needs to be a little bit more careful than with the principal chiral model in this case. And the reason for this is that, well, first of all, to deform these models and while retaining the local HR invariance, one needs the Tuco cycle to vanish on H. And this in turn implies that D should be a map between M and H in the symmetric case. And also this should be augmented by D being a map between P and Q in a semi-symmetric case. And an additional kind of complication which requires some extra care is the fact that the gauge fixing is not as kind of smooth as it was for the principal chiral model, because in general, one will have to gauge fix not only the coordinates, the extra coordinates of the initial model, but also some of the Lagrange multipliers. So this procedure can be done. There has been Spestos and Thompson, I think they consider some techniques to do this. So it's something that can be done, but still it needs some a little bit of extra care. And then finally, there is the obstruction that I also mentioned in the title, and that I will now also mention more in the next slides, which is that of integrating out the gauge fields omega. And in this case, one encounters a potential obstruction to the dualization, which comes as a result of the right local right invariance of the right action invariance of the action, which basically is lacking terms lying in the H subspace and basically doesn't allow to solve in general the equations of motion for these gauge fields, and so somehow forces a case-by-case analysis of these models. So what we did basically is proceeding trying to proceed in the most general way that we could. So we tried to isolate this potential obstruction, to confine it to a single equation, and we did it by basically solving the equations of motion in all the subspaces in which we could solve it, and substituting the solution back into the action and basically obtaining kind of a hybrid action, which still contains some information about the gauge fields in the H subspace, but still this somehow gives a sufficient gives enough information to find again to rederive the exchange of Maurer-Cartan equations and equations of motion, and to write down the T-dual Lax connection. And then one really needs to perform the case-by-case analysis in order to see whether these gauge fields can be integrated out or not. So if we start again from the master action for semi-symmetric spaces, you see this is just basically the action that I showed earlier with this deformation term and the Lagrange multiplier terms, where now this J omega is just the covariantized J projected on the four subspaces. So basically this is just the principal chiral model action, except that now the principal chiral model J omega star J omega is replaced by these MM and PQ terms. And the equations of motion for the gauge fields take this form here. And we see immediately from this equation of motion that we have terms in M, P, and Q. The inner term is in M, P, and Q, but there is no term in A, simply because we didn't include it in the initial action. And so this results in the fact that we can solve in general the equations of motion in the subspaces M, P, and Q, but we cannot generally solve the equations of motion in H. These take this form that you see here. And there is no kind of linear term in A tilde, sorry, it's just another name for A omega. There is no general way of solving this equation. So one needs to take care to perform a case-by-case analysis. So nevertheless, one can substitute back the solutions for P omega, M omega, and Q omega into the action and obtain this sort of hybrid action that I mentioned, in which you see there is still this information regarding A tilde, but all the remaining quantities are only written in terms of the multipliers. So here I shortened a bit. Well, I shortened the notation. We defined some quantities in order to shorten the notation, because otherwise the action would be quite ugly. And these Rij are just the entries of two operators, which map P to P or P to Q, Q to P or Q to Q, depending on the indices here. And And these appear basically when solving the equations of motion in P and Q, where they only depend on ad lambda h and d lambda m. And well, these, as I said, again, if we remove whatever lies in P and Q, we recover the hybrid actions for the symmetric spaces, basically, as I said earlier. And then there is this one form T, which basically represents the generalization of the principal chiral model, and again of the symmetric spaces, because it has an initial term, which is this one here, that one finds in symmetric spaces, and then receives contribution for P and Q subspaces, in which there is this Rij, which acts on lambda P and lambda Q. And similarly, this S operator, again, is just a generalization of the principal chiral model and of the symmetric space. And again, its first term is ad lambda h, but then it also contains contribution from Rij and ad lambda P and lambda Q. Okay, so if we now compute the variations of the action with respect to the multipliers, well, the equations of motion take this Maurer-Cartan-like form, in which basically we have Maurer-Cartan equation of the initial model with replacements of A, P, M, and Q with the tilde, with their tilde version, where the tilde version are nothing but the ones that the quantities that we obtain by solving the equation of motion in P, M, and Q. And while variations with respect to the tilde give back the unsolved equation. And if we combine all this information, again, we find, thanks to Jacobi identities, we recover the equation of motion of the initial models, which are replaced by this, in which the P, M, and Q are replaced by this tilde version, by their tilde version. So again, this exchange in role of equations of motion Maurer-Cartan equations allows to write down the T-dual Lax connection formally in the same way as it was written for the initial model by replacing the A, P, M, and Q with their tilde. Okay, so let me now go back to these potential obstructions that I was mentioning. Okay, I'm afraid I will be 5 minutes late. Okay, as I said, this equation of motion in H cannot be generically solved, cannot be solved in full generality. Nevertheless, if one solves the equations of motion in P, M, and Q and substitutes the solution back into this H equation of motion, this can be recast into this form that you see here. Now I will tell you what these W, Z, and zeta are. You see that this explicitly doesn't have any linear term in A, which allows for the general solution. And this is the structure of W and Z, these two operators which act only on the H subspace, on the H subalgebra. And this zeta here, it's one form which again takes values in H. So these are maps from H to H, and this zeta takes values in H. And here these ad lambda h and ad lambda m are kind of explicit in the bosonic multipliers, and these n, m, and l are operators which involve the fermionic contributions. So I kind of packed this in this way in order to highlight the bosonic contributions, and in such a way that if one wants to recover the operators for the symmetric case, one can simply just set this n, m, and l to 0, and the operators immediately become those of the symmetric spaces. And this is the form of L, as I was mentioning, with the contribution from P and Q and this Rij. So the feature of this equation is that this depends, the possibility of solving for a tilde now depends on the invertibility of these two operators, W and Z. And the thing is that one can rewrite this equation by exploiting the projectors on the worksheet projectors. And this basically can be written in terms of these two equations, the projection on the plus and on the minus subspace. And basically one can see that the equation can be solved for A if both the combination W plus Z and W minus Z turn out to be invertible. So it's not the invertibility of W or Z itself which is relevant in this case, but it's the combination of W and Z, the plus and minus combination of these two operators. And this is kind of an interesting feature that somehow, at first I was a bit puzzled by, because in the first model I studied that I will now describe, these two operators turn out to be both not invertible. So I was at first a little bit confused by this. And then I just realized that this property of projecting this equation on the two subspaces, and I realized that it's actually not the the operators themselves which matter, but it's their combination. So this model that I'm talking about is this three-sphere model, SO4 mod SO3, which is kind of well known in the literature. This was dualized, I think, in this paper by Festus, Thompson, Lozano, and Colgan in 2011. And this is so well known for being T-dualizable. It has also been studied in other papers. I think also in a paper by Linus and Ricardo, they gave some analysis of this model. And well, the thing is, one can identify in this case the subalgebra H and rewrite the generators in this way, so that one finds a nice set of commutation relations. One recovers the commutation relations of the symmetric spaces, and basically now studying the potentially obstructing equation reduces to the fact of basically computing a bunch of commutators and seeing how these operators act on the gauge fields. So, well, I should say that here in this case, I'm considering the gauging of the full group or SO4 of isometries and setting the deformation to 0 for simplicity. So the multipliers take values in the full SO4 algebra and the gauge fields in SO3. So if we compute this set of commutators that I was talking about, we can compute easily the action of W and Z on A tilde. And we find immediately that, well, at least for W, it is kind of easy to see that we see that this operator Wij, the Wjk, which would be this Fi epsilon ijk, this is non-invertible because this is just a 3x3 antisymmetric matrix. And similarly for Z, this is maybe less clear from this expression, but this also has a non-trivial kernel. If we contract this with xi, this vanishes. So these operators are both non-invertible, and as I said, at first I was a bit puzzled by this because I knew this model was T-dualizable, so I was a bit confused. But then, yes, it is indeed their combination which actually matters to the aim of dualization. And indeed, one can explicitly see that if by combining W plus and minus Z, the operators are immediately can be immediately inverted by taking an ansatz which is written in terms of these xi, yk, and epsilon. So the dualization in this sense it's pretty simple and can be performed kind of analytically without the need to invert any matrix. And the reason is basically the result of this kind of confinement of the potential obstruction to this H subalgebra equation of motion, which is something which is slightly different as compared to what was originally done in the literature, because as far as I remember, in the literature, people consider the inversion of these full 6x6 operators, and they used a slightly different technique to perform the dualization. So in this case, one doesn't need to invert this kind of 6x6 matrix by using, for example, Mathematica or whatever. One can really do this analytically by constructing an ansatz. Okay, and now there is another quick model, another model that I wanted to quickly describe, which is this OSP1/2 mod SO1,1. As I said, this is the model which describes super ADS2. It's a semi-symmetric coset, which is of the Green-Schwarz-like form. And this is basically what Verlinde considered in the paper from 2004 that I was talking about earlier. And this is what hopefully we will manage to find in the dualization, in the dual model to the principal chiral model. And so again, in this case, this is the OSP algebra, and again, we perform the gauging of the full isometry group, and we set the deformation to 0, so that one can expand the Lagrange multipliers and the gauge fields on OSP and SO1,1 respectively. And again, the study of these operators reduces to the study of a set of commutators, which is maybe a bit more tricky than in the S3 case, but still can be done kind of easily in this case because the gauge field is the SO1,1 is abelian, so it's kind of simple in this case. And indeed, one finds that in this case W on A is 0, while Z gives this kind of simple factor which can be easily inverted because you see here we have this fermions which contribute with this theta plus theta minus kind of theta squared term. So we kind of know we know immediately how to invert this this operator, and we can indeed compute the dualization we can go, the dualization goes through. We can really compute it. Okay, so I guess this is yes, this is all I wanted to say about this obstruction. Now let me try to wrap up a little bit and give some potential some potential next steps, which I kind of already mentioned. So as a quick summary, we try to focus on this super non-Abelian setting, which is, as I said, still the least studied and understood in this canonical point of view on T-duality. And we try to do this by considering dualization of super non-Abelian isometries for three classes of models: principal chiral models, symmetric and semi-symmetric spaces. And we isolated this potential obstruction that I was mentioning, which occurs in this coset models. And we also worked out explicitly exchange in role of equations of motion Maurer-Cartan equations and constructed the dual Lax connection exploiting this fact. And then as a prime example of this, we, since this was the initial aim, somehow constructed some explicit example to better understand the topic, to gain a better understanding of it. We studied this OSP1/2 principal chiral model, and we observed that T-duality seems to break the compatibility with supergravity by either dualizing the full group OSP or its bosonic subgroup SL2. So in terms of outlook and possible developments, well, some of them, as I said, I already mentioned. Somehow, for the principal chiral model on OSP1/2, we really hope to gain a better understanding of this breaking pattern and to be able to say something concrete and hopefully something interesting on this breaking pattern. We hope that something will come out in the next few months, and hopefully we'll find some matching with this Berlin action. And also, as I said, it would be interesting to consider the more complicated model, which would be the case of a 3D Greenwich bar superstring sigma model. This would certainly be interesting to study and possibly to compare with. And from the more general perspective, I think there is one kind of another interesting point, which I personally find interesting, at least, which would be basically the possibility of studying in more detail this obstructing equation, and ideally, I would say to try to see whether the invertibility condition for these operators, whether one could extract some invertibility condition for this operator W plus and minus Z, and trying to see whether these invertibility conditions might be used as kind of a classification technique, in a sense, to for models which can be or cannot be T-dualized. So I think this would be interesting, as would also allow to give a kind of a systematic study of which models can be and cannot be consistently T-dualized. Okay, and then, well, certainly it would be interesting to complete in full details the dualization of this OSP1/2 mod SO1,1 model. As I said, I already started this studying this. Then, well, at some point I had to write my thesis, so I had to stop working on this. But since this also will hopefully pop out in this dualization of the principal chiral model on OSP1/2, well, one may actually even hope that in future it could be possible to perform another T-dualization, for example, on the T-dual model. So performing a chain of dualizations, this could also lead to something interesting, hopefully. And then finally, well, it would be nice to consider more complicated example of symmetric and semi-symmetric spaces. We also kind of tried at some point to work a little bit on the symmetric cases, in particular on the superspace models of the symmetric type, particularly superspheres. But we had some kind of a bit of trouble with that, and so we decided to postpone this work some later stage, and this will also hopefully be an interesting next step to take into account. But certainly there are other semi-symmetric spaces that it would be very interesting to take into account also from the physical point of view. some spaces which appear in the ADS, in the context of ADS CFT correspondence. So there is kind of quite a few applications that one could try to consider. Okay, so I guess this is all I wanted to tell you about this. Sorry for going a little bit over time. I thank you very much again.
No, we thank you. Thank you for the nice talk.
Thank you.
And I know some people have to leave by 5, so please.
Yeah,
feel
actually,
free
also
to,
myself.
Yeah, so please feel free to ask questions. And yeah, Danielle, we will not keep you here for too long if you have to go.
Sorry,
So.
I'm terribly sorry because yes, I have this meeting at school because we're having the final meetings to give marks to the students, so they
Yeah, of course.
they always place this in the middle of the afternoon.
So do we have any questions? Maybe some quick ones. Oh, so if not, then I just wanted to ask some clarifying question. So these obstructions you are talking about, they are obstructions to just the existence of the T-dual model, right?
Yes, to the possibility of completing the dualization procedures, yes.
And then even if they are satisfied, then you have to check, for example, the integrability or the supergravity conditions also separately, or are they connected together?
I would say the integrability is kind of ensured, also by the fact that T-duality is not supposed to spoil this. And concerning the supergravity properties, well, in certain backgrounds, like in semi-symmetric spaces, it has been shown that the dual models should still be supergravity backgrounds, or should at least satisfy the generalized supergravity equations of motion. So one should still find something interesting, at least in this semi-symmetric or in general in Green-Schwarz models. But the thing is that, yeah, it is one is not a priori sure whether this dualization procedure can effectively be carried out, because this that there is this potential obstruction which rises, and hopefully one could be able to, this is what I was mentioning earlier, hopefully one could be able to extract some condition, some algebraic condition that the algebra should satisfy in order to be able to really complete the dualization. I think it would be an interesting point to clarify, because again, we kind of give an organizing principle in a sense, would kind of tell you which models one could effectively dualize or not. So yeah.
Mm-hmm. And even in the cases that this obstruction is sort of not satisfied, that you cannot find the T-dual model, is there something you can do? I think in the beginning you showed some transformation of the Filbine that could fix something, but still not everything.
But the thing is that if the obstructing equation cannot be solved, well, at the moment I would say, well, the procedure cannot be completed, so one cannot integrate out the gauge fields in the H subspace. So I would say that the T-dual model, it's not really kind of reachable in this sense. Maybe there is some other technique that one could possibly exploit or try to consider. I don't know. This is something I've never thought about. I know maybe one could, for example, consider the BRST techniques. This is something that has been considered in the literature, for example, in the paper by Grassi and Mezzalira, which I also mentioned at the beginning. But yeah, I don't know. I would say at the moment, yeah, the procedure cannot be completed. So I don't know whether one could engineer something to circumvent this problem. Hopefully, yes.
Yeah, okay, well, thanks. So are there any other questions or comments? Okay, so if not, then let's try to thank the speaker.
Thank you.
Yeah, you can unmute and we'll do some clap.
Thank you very much.
Yeah, thank you very much. And I guess we'll have Daniele speaking next time. I'll figure that out. And also, Danielle, if you want to join.
Yeah, that's what I was going to ask you, actually.
Definitely invite you.
Thanks very much. Yeah, please share the link. I would be very happy to attend if I can.
Yeah, I'll write you an email.
Okay, thank you very much.
Yeah, thank you for the talk and good luck in the future.
Thanks. Good luck to you as well.